This is a video that's going to work through an example of universal gravitation. So universal gravitation works between any two objects with mass, and I'm going to do this. I'm going to say we have a planet like this, and let's give this thing, well, let's make this be the Earth. So the Earth has a mass of about 6.4 times 10 to the 24th kilograms, and it has a radius the Earth has a mass of about 6 times 10 to the 24th kilograms. And out here I'm going to put the moon. And the moon has a mass of about 7.3 times 10 to the 22nd kilograms. And then we just need the distance between the Earth and the moon. When we are doing these distances, we are always talking about a center-to-center distance. So this is a distance of 384 million meters. And maybe what I would like to know is find the force Earth exerts on the moon. Here we go. The force between these we know is going to be Gm over r squared, so I can actually put in these values. Now I'll give you another problem to work with this too, because this isn't a very complicated problem. But it's good to be able to just figure out how to use the formula in the first place. There's the mass of the Earth. There's the mass of the moon. And we'll divide by a distance that is really big. When I do that, I end up with a value of about 2 times 10 to the 20th newtons. So a 2 followed by 20 zeros. That is a huge amount of force. But consider this. The acceleration that the moon feels, we know mass times acceleration equals force. So if we want the acceleration, that's going to be a force over a mass. That's going to be our 2 times 10 to the 20th newtons divided by 7.3 times 10 to the 22nd kilograms. And that works out to be just shy of 0.003 meters per second squared. That's the acceleration on the moon. Not the acceleration on the surface of the moon. That's the acceleration that the moon experiences due to the Earth. The acceleration that the Earth experiences due to the moon is going to be even smaller. We've got the same force. Newton's third law says we get the same force, but now we're dividing by 6 times 10 to the 24th kilograms. So the force that the Earth feels from the moon is also big, but the acceleration that the Earth experiences due to the moon is even smaller. It's going to be 1, 2, 3, 4 with a 3 meters per second squared. These are accelerations that are small enough that we should be writing them in scientific notation. 3 millimeters per second squared, and this is going to be 3 times 10 to the negative fifth meters per second squared, so 30 micrometers per second squared. These are really small forces, or accelerations rather. The other thing that we can do with this is to say there is some point or other where if I'm traveling from the Earth to the Moon, there is some point, let's say here, where I'm balanced, where I feel no net force at all. If I dropped into that location, I would stay put. That's an interesting question, and we're going to mess with that one real quick. I'm going to say that this distance from the Earth to that point can be x, and then the remaining distance to the Moon is going to be r minus x. So I'm going to draw a free body diagram for my spot. Now it would be maybe a little bit convenient if there was something in that spot. So I'm going to put a person, and I will do a free body diagram for my person. We've gotten so very used to the idea of drawing a gravity vector right away. We don't have to do that in the downward sense, but now we have two gravity vectors. We're going to get one force that points to the left, and that is a force from the Earth, and we're going to have a force that points to the right, and that's a force from the Moon. We can pick a direction to be positive, and I'm going to call to the right positive, just out of habit, really. There is my free body diagram. My person can have a mess, if I want, I suppose. It's going to cancel out, so call that mass person. Might as well include it for right now. What I have then, when I do my sum of forces equation, I have force from the Moon to the right, force from the Earth to the left equals mass person times acceleration. If I'm looking for that equality point, equivalence point, that one's going to be 0. If I'm looking for that equivalence point, that one's going to be 0. Force from the Moon, that is g times mass of the Moon, mass of the person, over, and I'm just going to start off by saying distance from the person to the Moon squared. That's part of what I'm looking for. And then minus the force from the Earth, so g, mass of the Earth, mass of the person, over distance between the person and the Earth squared equals 0. If that equals 0, that means these two are equal to each other. I can cancel right away g, which is nice because I don't have to put in those exponents. I can cancel the mass of the person, and that's good to be able to cancel. The distance from the person to the Earth, that's the distance that I had called x, and the distance from the person to the Moon, that's the distance that I had called r, which is the distance between the Earth and the Moon, minus x. So I'm going to put those values in. Mass of the Moon over r minus x squared equals mass of the Earth over x squared. And now all I have to do is solve for x. So I just need to solve this thing. Now I can do a couple of different things with this, and I imagine your immediate thought on this thing is to cross multiply it, so I will follow suit. I see this thing and I'm going to have to expand that. I'm going to divide by me first so that I can not have that carried along and distributed through a lot of terms. So now when I distribute this, I get r squared minus 2x r plus x squared. Now I'm going to take all my x squared, or all my terms really. I've got an x squared, an x, and a non-x. I'm going to just move everything over to the same side. So over here on the left, I will have 0. On the right, I'm going to have an x squared. I have an x squared, and I'm going to subtract this over and factor it out. So 1 from the x squared minus over me. Got a term with just x, and that is times negative 2r. And I've got a term with no x at all, and that is just r squared. This thing looks like a quadratic equation. Here's my a, here's my b, here's my c, and I remember that the r that I need to plug in, so let me grab these values. I've got an r, or I've got a mass m, mass earth, and r that all need to go into this equation. R is 384 times 10 to the 6th meters. Mass of the moon, 7.3 times 10 to the 22nd kilograms. And mass of the Earth, 6 times 10 to the 24th kilograms. So when I punch all of that into a quadratic equation, I end up with an x value of 3.2 times 10 to the 8th meters, and I get a second answer of 4.7 times 10 to the 8th meters. And now I have to think about this a little bit. Are these answers reasonable? 3.2 times 10 to the 8th, the distance between them, so this is I could rewrite this as 3.84 times 10 to the 8th meters. When I grab that 3.2 answer, that 3.2 times 10 to the 8th number puts me about here, which is great, and that works well. So if I want the distance between the two where I can be, and I'm going to be steady, that makes sense. 4 point something times 10 to the 8th puts me out here. There's a spot where mathematically I have an equal amount of force from the moon and the earth out here somewhere, but both of those would be pulling inward, so that answer doesn't make sense. I've got to go with the one that fits in between. So what I want is this number. That is solving a good problem with universal gravitation. It's exactly the kind of problem that you'll end up solving in Physics 2 with electricity. So if you are hesitant about taking the time to really learn this, it will come back around a second time. This is very much worth the time input now.